So today I'm going to start with the chapter 13 comprehension checks. Number 8 is also a calorimeter problem, except this time your unknown is not in the metal, your unknown is in the liquid. So we have a calorimeter and it has 150 grams of a liquid. It doesn't tell me water this time, so I don't know what it is. And though it tells me it's at 23.7 degrees Celsius, I'm taking 25 grams of metal copper, and that has been heated to 70 degrees Celsius, and I'm sticking it in the calorimeter. The final temperature is 25.3 degrees Celsius, and the question is wanting you to know, find C, or the specific heat for the liquid. So we're doing the similar thing, but we're doing it for the liquid, not for the object. And so I cannot first calculate. Last time, the first thing I did was I started working on for the water, and I'm not going to do that this time. They do tell me a hint. They say to ignore the calorimeter. So before I can find C for the liquid, if I was to want to put all these things in for C for the liquid, I would need to know the mass, which they tell me, and the temperature difference, which I have, but I don't have a way of knowing Q. So I first need to figure out the Q for the liquid. So to know the heat that goes into the liquid, I would need to know the Q for the calorimeter, but we're ignoring the Q of the calorimeter. So the other thing I would need to know is Q for the object. So can I figure out this equation for the object? And I can, because I know the mass, they told me the specific heat, and I know the temperature difference. So I'm going to figure out the heat for the object first. So the mass of the copper is 25 grams. The specific heat is 0.386. And the temperature difference for the copper is it goes from 70 to 25.3. So you would say 25.3 minus 70. Your temperature difference is negative 44.7. So you're just going to multiply 25 grams times 0.386 times negative 44.7. And you should get a Q. Remember, this is for the metal or the object. Negative 431 joules. And that makes sense to me. The metal is losing heat, so it's going to have a negative number for its heat. Now, we know that the negative of the object is the liquid. So whatever the object is losing, the liquid is gaining. So the Q for the liquid would then be just the opposite, 431 joules. Now, I'm still trying to figure out if I can get everything needed to calculate this equation for the liquid. So I have found the Q for the liquid. I know the mass of the liquid. I don't know C, but that's what I'm looking for. And I can calculate the temperature. So we just did all of this was for the object. So now let's do it for the liquid. Q is 431 joules. The mass of the liquid is 150 grams. I don't know C. And then the delta T for the liquid, well, the final is 25.3, and the initial was 23.7. So you're going to do 25.3 minus 23.7. You get 1.6 degrees Celsius. So I'm going to rewrite this equation to solve for C. So I'm going to basically divide by the 150 and the 1.6. And when you put that in your calculator, you get 1.8 joules over grams degrees Celsius. And if I wanted to, I could try to go look that up to see what that liquid is. So I'm just going to recap because that was really confusing. You have a calorimeter, you don't know how much, you know how much liquid is in it, but we don't know what the liquid is, and we're sticking a chunk of copper in it. And so what is happening is the liquid is going up. So what happened is we were not able to calculate at first all the information to figure out the specific heat of the liquid. In order to do that, we need to know the energy that went into the liquid. So we actually had to calculate the energy that went into or that left the metal. So we did the Q equals MC delta T for the metal, because if the metal lost the energy, that is the energy that went into the liquid. And so once I was able to calculate the heat that left the object, I was then able to figure out the heat that went into the liquid. Once you knew the heat that goes into the liquid, the Q, we were able to figure out the specific heat of the liquid. For question number 9, I didn't write down the whole question, but it tells me a 300-gram sample of an unknown metal is used in a calorimetry experiment. The calorimeter holds 1,200 grams of water, and it starts off at an initial temperature of 25 degrees Celsius. And the metal, I wrote the TI, or the initial temperature of the metal, as 136.3 degrees Celsius, and then it's put into the calorimeter. The experiment stops when the water hits a final temperature of 27.3 degrees Celsius. And then it tells me that the heat capacity of the calorimeter is 1,100 for this experiment. So this is similar to the problems we were just doing, just we cannot ignore the calorimeter. So in the past, when we were doing the Q, we were actually ignoring the heat that the calorimeter can absorb, but we cannot do that for this equation. I'm wanting to know the specific heat of this metal. So if I was going to use the Q as MC delta E of the metal, I would need to know the heat that the metal or the object took in, the mass, which I do know, the C, which I do not know, which I'm looking for, and the temperature change, which I can figure that out, but I do not know the Q. And if you'll know, the Q of the object is equal to the Q of the liquid and the Q of the calorimeter. So in order to find this, I have to find the heat that goes into the liquid. To figure this out, I think I can figure this out. I have everything for it. I have the mass of the liquid. I have the C because the liquid is water, and I know that, and I have the delta T. So first, let's figure out the heat that goes into the liquid. So I don't know the Q, but I do know that I have 1,200 grams, and I know that it's water and the specific heat of water. And the temperature change. So the final temperature is 27.3 and the initial is 25. So it's 27.3 minus 25 is 2.3. So you actually get a Q for the liquid, or for the water, 12,000. I'm only going to use 2 significant figures because I only have 2 significant figures in my information going in. Remember, the whole point is to know the heat that came out of the metal. So I know that there's 12,000 joules going into the water, and this calorimeter actually also takes in heat. Now let's figure out the amount of heat that's going into the calorimeter. So if I'm trying to find the Q for the calorimeter, when they give me the specific heat in the calorimeter, they actually just give it to me as joules over degrees Celsius. That's actually a heat capacity unit, and there's no mass to that unit. So I'm not going to worry about mass here. The mass calorimeter does not matter. The whole calorimeter has the heat capacity that they're telling me. So I'm going to say Q is equal to the heat capacity that they gave me times the temperature of difference, which is 2.3. So Q equals, Q of the calorimeter is 2,500. So they gave me what's called a heat capacity. A heat capacity does not have a mass in the unit. It's just the amount of heat that goes into the whole calorimeter. So when I'm figuring out Q for this, I'm actually going to take the mass out. And so you have what they gave you of the heat capacity times the temperature difference, and you get 2,500. So I know that there is 12,000 joules going into the liquid and 2,500 joules going into the calorimeter. If I add the heat in the liquid and I add the heat in the calorimeter, that is the heat from the object. So I have 12,000 plus 2,500. This is where everybody gets confused because yes, technically that equals 14,500, but I only have two significant figures here. So I'm gonna have negative 15,000 joules coming out of the object and into the liquid in the calorimeter. Now that I know the total amount of heat that is coming out of the object, I can figure out the specific heat capacity for the object. So the total Q for the object was negative 15,000 joules. The mass of the copper, or of the metal, sorry, not copper, it's 300 grams. I don't know C. And the temperature difference, so is going to be from final, which is 27.3, minus the initial, which is 136. So you're gonna have a negative. That makes sense because the object is losing heat. And I get negative 109. I know that's messy. It's all crammed in there. So I'm going to rework it. So if I take negative 15,000, I divide it by 300 times 109. Specific heat capacity of 0.46. That's a really long problem and a really complicated problem because we had to figure out the Q for the liquid, the heat in the calorimeter, and in order to figure out the heat of the object. Question number 10 is a latent heat equation. This question to me was really confusing to even figure out where to start, but I didn't tell you the latent heat equation yet, but latent heat is basically heat that is absorbed or released when you are changing phases. So either going from a solid to a liquid or a liquid to a gas. And the equation for when you are changing phases is Q is mass times L. And L is given to us as LF, which is L of fusion, which happens when you're like melting between solids and liquids. And then LV, which is vaporization, which is when you're going from a liquid to a gas. They tell you LF and LV. So there's 3 steps to this. So basically we have a sample of ice and we're starting at 0 degrees Celsius and we're converting it to vapor at 100 degrees Celsius. So the 3 parts of this are the melting of the ice, then heating of the water, and then the vaporizing of the water. So we actually have to figure out the heat transfer at all 3 of those phases and then add them up to know the total heat that it took. So the first part, while you're melting the ice, you're just changing phases. So we're gonna use latent heat. So this part, I'm gonna say melting so that we stay a little organized here. And latent heat, we're gonna use Q equals ML. I'm looking for Q, I'm looking for the heat. I know the mass is 300 grams. And then the L, since this is LF, or latent of fusion, because we're going from a solid to a liquid. So times 334. Grams cancels out, and we're left with joules. Now we need to keep our answer in 3 significant figures. So I'm gonna write it in scientific notation so that my answer keeps 3 significant figures. And so this is the heat that is required at first to melt the ice. So now let's do the next step, which is when we have to heat it. Now when we actually have our 0 degrees water or just above and we're heating it to 100 degrees Celsius, we are actually not doing latent heat because we don't have a phase change going on. So we have to just use this Q equals MC delta T equation. I don't know Q. I do know the mass. I do know the specific heat of water just because it's right there in pink. And the temperature change is 0 to 100. So it would be 100 minus 0, which is 100. So if I was going to multiply all this through, I get 125,500 joules. And this is the heat needed to raise the water temperature from 0 to 100. Third part is actually once it gets to 100 degrees, there is energy that is required for the water to change phases from a liquid to a gas. And that is where we're going to use the latent heat equation, which is just Q equals ML. So we're looking for Q, mass is 300. But this time the L we use is the L for vaporization. And it actually takes a lot, you'll see. And so it takes 678,000 joules once my water is already heated to go from being a liquid to a gas. So the three things we figured out is we figured out first when it's melting, then when we're heating it up, and then once it's heated for it to change phases again and to become a gas. So to find the total amount of energy that is required for that, I would actually, you're gonna take all three of these and add them up. And if you're sticking with three significant figures in your answer, you should get 904,000 joules. Question number 11, the very last one for the chapter 13 comprehension check says, when it comes to how kinetic and potential energy change, what type of reaction, an endothermic or an exothermic reaction, is similar to a skier going uphill? Well, I'm not a very good skier, but I do know that going uphill takes a lot of energy. You have to put energy into it. And so when we have two types of reactions, we have endo, which is heat can go into it, and we have exo, heat coming out. So I'm gonna think skiing going uphill puts energy into it, so it would be an endothermic reaction. Good job, guys.